Okay. So we're going to look first at the end of yesterday. So yesterday when we were solving, if we were going to factor something that was like a quadratic, then our trig functions had to match, right? If this was cosecant squared and this was secant, we wouldn't have been able to do what we did. But these two didn't match. Like I had sine and secant mixed, and that's fine as long as it's not a quadratic type of situation. If it's a GCF type of thing and you can still split them where you can solve them individually, it's fine. So I'm pointing that out because today we're going to have to substitute in some identities and then solve. So we have to make them solvable for ourselves, basically. And we have to kind of know how to think about what it is that we need. So let's look at some of these. And I'm going to make some assumptions as we go through this. I'm going to assume you know your trig values, which you should. I'm going to assume you know how to do algebra, which you should, and how to factor, because I'm not going to slow down and, work through that slow, because if you don't know what the sine of pi 6 is by now, I can't help you. I don't even know what to do about that. So I would rather spend time on the stuff that's different today and that matters. And I want to get through a bunch of different ones. So I'm going to go kind of quickly through most of that. I try and pare down how many examples we do and even how many homework problems you have. But in this case, I feel like you need to see a bunch of different things happen. If we didn't, we definitely wouldn't go through them all, but I think that's helpful here. So let's look at number 1. We've got cosine x minus 1 equals sine squared x. And I'm going from negative infinity to infinity. So I'm going to have the whole circle, and then I'm going to have to take into account the rest. So when I look at this, and I've got my cosine x minus 1 equals sine squared x. Well, I've got cosine and sine, and there's no GCF, so I feel like I got to fix something. So when we've got the squareds, most of the time we say, all right, I'm going to look at my reference chart. I'm going to find my Pythagorean identities and see if there's anything that helps me. So when I look at my Pythagorean identities, I could substitute for sine squared 1 minus cosine squared. I think that would be helpful. So let's do that. So this will give me cosine x minus 1 equals 1 minus cosine squared x. So now everything's in terms of cosine. That's good, because I have a quadratic. So since it's a quadratic and I want my squared term positive, I'm going to move everything over to the left. So this is cosine squared x plus cosine x. And then I'm going to subtract the 1 over there, so that'll be minus 2 equals 0. That's something I can factor. So I'm going to factor. When I factor these, I get, this is going to have to be cosine x, cosine x. This is negative, so the signs are opposite. This is positive, so the 2 has to be positive, and the 1 is negative. And it's factored. Okay? So then I can solve them. This side here, I will get that cosine x equals negative 2. So when on my circle does cosine equal negative 2? It doesn't, does it? What's the smallest number it could equal? Negative 1, right? Because we're going from negative 1 to 1. So the cosine, it'll never be negative 2. So this doesn't even make any sense. It's not that it's undefined. It's just that that doesn't even compute. It's not even part of the domain. So that helps me none. Then over here, cosine x equals 1. So around my circle, I know that cosine x equals 1 at 0 and at 2 pi and 4 pi and 6 pi and negative 2 pi and whatnot. So I'm just going to put my 0 because I'm going from negative infinity to infinity. So because of that, I would have whatever my angle is plus 2 pi n. Well, my angle is 0, so this is just 2 pi n. Okay. Any questions at all? Okay. And even though I'm going quickly, you could stop me to ask me a question. I might pass out if you did that, but you can. All right, number 2, 0 to 2 pi. So I'm using the whole circle, but I don't have to worry about the infinity thing. So I look up here. I've got a quadratic, but I can't factor it because the cotangent and the cosecant don't match, right? So I look at my chart. I find my Pythagorean identities since there's a square. Just because there's a square doesn't mean that's always what I use, but that would be the first thing I would check for sure. So cotangent and cosecant are related with the Pythagorean. That's good. So if I want to replace this, cotangent squared, that's going to be replaced with cosecant squared theta minus 1. And that's more than one term, so I'm putting it in parentheses. Minus 3 cosecant theta plus 3 equals 0. Everybody with me? So those parentheses, in this case, they're not necessarily important, but you don't always know when they're important. And if you got in the habit of really using them every time you substituted in more than one term, then you wouldn't forget them when it was important. Which maybe you're not doing that anyway, but some people are, because somebody always does. So here, when I combine my like terms, I get cosecant squared theta. Then I want to put them in order, so this will be minus 3 cosecant theta. Then I have a negative 1 and a positive 3, so that'll be plus 2 equals 0. So once I've simplified it, I've got it all in cosecants, which is good because it's a quadratic. Then I need to factor it. So this will be cosecant theta and cosecant theta. The last one's positive, so the signs are the same. This is negative, so they're both negative. It's a negative 2 and a negative 1. So then I'm going to solve these. So I get cosecant theta equals 2. I would rather think about sine, so I'm going to make that into sine theta equals 1/2. That's positive. Sine is positive in quadrants 1 and 2. And when sine is 1/2, my reference angle is pi 6. So I need my first quadrant pi 6 angle, which is pi 6, and my second quadrant, which is 5 pi 6. Okay. Then I need to take care of the other factor, so this will give me cosecant theta equals 1. I would rather think about sine, right? And then sine is 1 only one time around the circle, and that is at pi halves. So theta equals pi halves. Then I just need to put all my answers together, just like we did yesterday. I start with pi 6, then it's pi halves, and then it's 5 pi 6. Okay. Any questions at all? All right. Let's look at number 3. I'm going from pi to 2 pi. And so when I look at this, I always want to look at these algebraically first, because they're not always going to be split up like yes, go ahead. Yes. There you go. So when I look at this, there's nothing squared. I don't have a quadratic. I don't have a GCF. So then when I want to start thinking about my identities, since there's nothing squared, there's no Pythagorean identity. Nothing else jumps out at me. So I think I'm going to try my reciprocals and quotients. Okay, so that's not the first thing that we've been looking at, but here I think that's really kind of all I have, right? So I can make tangent into sine over cosine. So I can make that 3 sine alpha over cosine alpha minus 2 square root of 3 sine alpha equals 0. Since I did that, now I have a GCF. My GCF is sine alpha. So I'm going to substitute that out, or not substitute, I'm sorry, factor that out. That leaves me with 3 times 1 over cosine alpha minus 2 square root of 3 equals 0. Okay. So I would really rather not leave that as 1 over cosine. I would rather change that to secant. So this will give me sine alpha times 3 secant alpha minus 2 square root of 3 equals 0. So I factored out my GCF. I have two factors that I can actually solve here. So that means that I'm going to split these up, and then I can get sine alpha equals 0. So from pi to 2 pi, I know that sine is 0 on the x-axis, so it's at 0, pi, and 2 pi, but I'm only going from pi to 2 pi, so I'm going to use those. So alpha equals pi and 2 pi. Then here, got 3 secant alpha equals 2 square root of 3. So secant alpha equals 2 square root of 3 over 3. Instead of secant, I'd rather think about that as cosine. So that'll give me cosine alpha equals the square root of 3 over 2. And I know that I had 1 over cosine. We changed it to secant, and then we changed it back to cosine. But I didn't change it back to how it was, because if I left it like this to try to get it here, I'm afraid y'all are going to do weird things. I think it's better to put it here and then think about actually taking the reciprocal of both. All right, so then alpha, so I'm going from pi to 2 pi. Cosine's only positive of these two. It's only positive in the 4th quadrant. When cosine's the square root of 3 over 2, my reference angle is pi 6ths. So I need my 4th quadrant pi 6th angle, which is 11 pi 6ths. Then I put them all together, and I will get pi 11 pi 6ths and 2 pi. Any questions at all? All right. So let's look at number, did you have a question? No. Let's look at number 4. 0 to 2 pi, using the whole circle here. So when I look at this one, I want to think algebraically first. So don't have a GCF. I can't take the square root of anything. I don't have any quadratics. I can't just solve it as it is. So I'm going to have to think through some identities. But there's not a whole lot that these will do. Now, if I kind of did the same thing I did on number 3, and we're going to talk through it and think through it. And I know that because it's still new to you, you just thinking through it sometimes doesn't work so well because you're not, like when you're thinking about it, you're not seeing it the same way you would if you wrote it down. So there's nothing wrong with trying to write something down and be like, yeah, that didn't work. Let me try something else. And like I said yesterday, I mean, that's the same thing I do. I start and I'm like, oh, that was a bad idea. Let me try something else. So one thing we could do, and we're just going to think through it instead of writing it. If I could make this 1 over cosine, I can make this sine over cosine. If I did, then I would have a GCF that's 1 over cosine. The problem is you can't start factoring until you have set equal to 0, and we still have this 1 over here. So if I actually move this 1 over there, then that actually wouldn't be a GCF. You with me on that? So we're going to do something that's not something that you would probably think to do right off. That's why we're using it as an example. But secant and tangent are related on here, I mean, in a few different ways. But one of the ways is the Pythagorean identities. And I know that these are not squared, but we could probably do something to make it where we could use it. So I'm going to move this tangent over to the right so that I get secant x equals tangent x plus 1. So just like one of the processes you can do to solve something is you can take the square root of both sides, you can also square both sides. But there's a little catch to that. Okay, so we are going to square both sides, but we're going to put a little star here because when you do that, there's something extra we have to do at the end. So let's talk about what that is and why. When you take the square root of both sides, we have to put in a plus or minus, right? Because let's say we take the square root of 4. Well, we don't know if that came from negative 2 squared or 2 squared because it could have been either one, so we have to take into account both, right? Well, if I square this, and then we solve, and then at the end maybe I have to take the square root of it, and I put plus or minus, well, I know for a fact it wasn't plus or minus, it was just the positive one, right? So what we're doing by squaring it is we're introducing a whole nother set of values that may not actually work. So when we're done, because of that, we have to check our answers because there might be some extraneous answers. Does that make sense to you? So so that's the only extra thing is like we're going to go through and do everything, we're going to solve it, but because we did it like this to begin with, we have to go back and check our answers and then just mark out whatever doesn't work. So when I square this, I'm going to get secant squared x on the left side. On the right side, I do not get tangent squared plus 1. I get tangent squared x plus 2 tangent x plus 1. So now I've got squared stuff. So now I can actually use those Pythagorean identities since I didn't have really any other option. And I have to decide, do I want to substitute and remove tangent squared or substitute and remove secant squared? So if I substitute and remove this, I'd be introducing some secant something. And that's fine because there's a secant over here, but I still have this tangent and I would still have a problem. If instead I substituted this with something that had tangent, then everything would have tangent, and I feel like that's a better choice. So when I look at my Pythagorean identities and I find secant squared, that's equal to tangent squared plus 1. So that's what I'm going to substitute in here. I'm going to make this tangent squared x plus 1. So that's equal to, then I rewrite all this, tangent squared x plus 2 tangent x plus 1. Then when I start to simplify, things start working out nicely. So I've got, when I subtract tangent squared from both sides, those zero out. When I subtract 1 from both sides, those zero out. So is here where I lose my equal sign and start making up math? No, because that should never happen. I still have something on the left-hand side of the equal sign, and that is 0. And that's equal to, on the right-hand side, 2 tangent x. Need to get tangent x by itself, so I'm going to divide by 2. So I get 0 equals tangent x. Then when I go back and look at my circle, I know that tangent is 0 on the x-axis, so it's 0 at 0, pi, and 2 pi. And because of the interval they gave me, I got to use all of those. So x equals 0, pi, and 2 pi. But before I box that and move on, remember I have to go back and check my answers. So I check my answers by substituting these back into my original equation. So I'm going to start with 0, and I'm going to substitute it in here, and that's going to give me secant 0 minus tangent 0 equals 1. And I need to see if that's a true statement. If it's a true statement, I'm good. If it's not a true statement, I can't use 0. Secant is the reciprocal of cosine. Cosine of 0 is 1, so secant of 0 is 1. Minus tangent of 0 is 0, that equals 1. So I get 1 equals 1, that works. So 0 is a legit answer. Then I have to do pi. So I'll get secant pi minus tangent of pi equals 1. So again, secant's the reciprocal of cosine. Cosine of pi is -1, so secant of pi is -1. Minus tangent of pi is 0. That equals 1. So I get -1 equals 1. That is not true. So I do not like pi. And I mark it out. Then I have to check 2 pi. Because basically either all of them could work, none of them could work, or some of them could work. So you still have to check them all. So now I'm going to try secant of 2 pi minus tangent of 2 pi equals 1. So cosine of 2 pi, I'm really back at 0, so I get the exact same value. So the same thing's going to happen that did up there. 1 minus 0 equals 1, 1 equals 1, and we like that. So this is my answer. And you don't have to rewrite it. Actually, I like it better like this, because what this shows me is you actually found them all, and then you checked them and realized that one didn't work. So it's fine to have it like that. Okay? Y'all are likely to start getting an Amber Alert, because mine's coming through. I don't know. All right, any questions? We good? Okay, so do you have to check your answers on all of them? No, only when you start by squaring both sides, right? I mean, you can check them on all of them, but you don't need to. I wouldn't. All right, so let's look at number 5. I'm going from 0 to 2 pi. That's a whole circle. And when I look at this algebraically, don't really see much I can do, but I do see a double angle in there, and that's something I'm definitely going to want to get rid of. So I'm going to go find my double angles on my reference chart. I find sine of 2 theta. I don't have to make a decision because there's only one, and that's 2 sine theta cosine theta. So that's what I'm going to substitute in right here. So this is going to be 2 sine u cosine u plus 4 cosine u equals 3 cosine u. Okay. So I do have a sine and a cosine, but I don't think that's going to be a problem because if I subtract this from both sides, then that'll just take care of this, and then I will have a GCF. So I think it's going to be fine. I'm going to rewrite this. 2 sine u cosine u. When I subtract 3 cosine u from both sides, that'll just leave me with 1, so it'll be plus cosine u equals 0. I have a GCF, so I want to factor that out. Factor out that cosine u. That leaves me with 2 sine u plus 1. All that equals 0. Okay. Then I can solve. I will get that cosine u equals 0. Well, cosine equals 0 at pi halves and 3 pi halves. So u equals pi halves and 3 pi halves. Then I solve this one. 2 sine u equals -1. Sine u equals -1/2. So on the circle, sine is negative in quadrants 3 and 4. When sine is 1/2, my reference angle is pi 6. So I need my third quadrant pi 6th angle, which is 7 pi 6, and my fourth, which is 11 pi 6. Then I'm going to put them all together in order. That means I would start with pi halves. Then my next one would be 7 pi 6. Then, oh, well, that makes no sense. My brain and my hand don't always agree. Oh, come on. 7 pi 6, and then I'd have 3 pi halves, and then 11 pi 6. So go ahead and, there we go. 7 pi 6, 3 pi halves, 11 pi 6. And that's my answer. Okay. Any questions? All right. Let's look at number 6. Here I'm going from pi halves to 3 pi halves. Right there. I have cotangent of 2 theta times 2 tangent theta. Cotangent and tangent are reciprocals of each other, but that does not multiply to give me 1 because one of them's 2 theta and the other one's theta. So those aren't exactly the same. So I want to replace that tangent, that double angle, cotangent of 2 theta. So I find my double angles. On my double angles, there's no cotangent. But since cotangent and tangent are reciprocals, I can use the tangent of 2 theta. I just use the reciprocal of the identity. And before I write it down, I remind myself, again, I'm using the reciprocal, so I actually write it down the correct way and don't just copy it off of here. So this would give me 1 minus tangent squared theta over 2 tangent theta. Then I'm going to multiply that by 2 tangent theta, and then plus 2, and that equals 0. Okay. So this is going to work out kind of nicely because I see some things that are going to cancel out. These are going to cancel out. That's going to give me 1 minus tangent squared theta plus 2 equals 0. So 3 minus tangent squared theta equals 0. Tangent squared theta equals 3. So tangent theta equals plus or minus the square root of 3. Okay. When tangent's the square root of 3, there's only 1 3, so my reference angle is pi thirds. And this is plus or minus. So in the second and third quadrants, tangent's either plus or minus. Doesn't even matter if I know which is which. So I need an angle from each quadrant. My second quadrant pi thirds angle is 2 pi thirds. And my third quadrant angle is 4 pi thirds. Any questions at all? Okie dokie. Let's look at number 7. All right, so I'm going from 0 to 2 pi, and that means I'm using the whole circle. I've got sine of pi 6 minus beta and cosine of pi thirds minus beta. When you look at your chart, it looks very similar to the cofunction identities, but the cofunction identities only use pi halves minus theta, so it's not those, and I don't want to try and force it down there. Instead, and it also says it right here on the left-hand side, I'm going to use my sum and difference ones, and those are in the bottom of the first section, okay? So I'm going to use this as sine of a minus b. So I find sine of a minus b on here, and then I'm just going to substitute. So this becomes the sine of pi 6 times the cosine of beta minus the cosine of pi 6 times the sine of beta. And that comes from sine of a minus b from that first term. Then I'm going to subtract cosine of pi thirds minus beta. So I look on here and I find cosine of a minus b. Then I substitute that. That's going to give me cosine of pi thirds times cosine of beta plus the sine of pi thirds times the sine of beta. Right here. The bottom of the first section on the left. Or on the right. Oh, yeah. Yeah, no. Sorry. No, the bottom of the, yeah, it's in like in 3 sections. That's okay. All right, so we've got square root of 6 over 2. So I got a lot of junk I wrote down, but it's nice when I can actually take the sine or cosine or whatever, an actual angle. I like angles in here that aren't variables. So the sine of pi 6 is 1/2, so this will give me 1/2 cosine beta minus the cosine of pi 6, which is the square root of 3 over 2, times the sine of beta, minus cosine of pi thirds, which is 1/2, times cosine of beta, and then minus again, because I used parentheses there like I was supposed to, sine of pi thirds, which is the square root of 3 over 2, times sine beta, that equals the square root of 6 over 2. Okay, so that cleaned it up some. And remember, the stuff that came from here, there was no magic. I didn't make anything up. I got it all from here. All right, so now when I look at this, I got half cosine b minus half, or I'm sorry, beta, half, and when those zero out. So that's good, they're gone. Then I have negative square root of 3 over 2 sine beta minus square root of 3 over 2 sine beta, which means I'm combining them since they're both negative, it'll be a negative something. And that's like 1/2 times the square root of 3. So I have half of a square root of 3 and another half of a square root of 3, and I put them all together, I get a whole square root of 3, right? So it's negative square root of 3 sine beta. That's equal to square root of 6 over 2. Don't make fractions weird just because there's square roots in them. All right, so now I need to get sine beta by itself. I need to divide by negative square root of 3. But remember, dividing by something is the same as multiplying by the reciprocal, so I don't have to make that into a fraction over a fraction. I can make this sine beta equals square root of 6 over 2 times the reciprocal of this, which would be negative 1 over the square root of 3. Then I skip that whole fraction and a fraction thing. Now, when I do this, I could put it all together, and it would just be negative square root of 6 over 2 square roots of 3, but there's no reason to rewrite it because we can simplify first. And when I do that, remember everything under the square, when you're multiplying and dividing, everything under the square root you can work together, and everything outside the square root to work together, but they don't mix and match. So since these are both under the square root, 3 goes into 3 once, goes into 6 twice. That's really all I can do with that. And so then that becomes sine beta equals negative square root of 2 over 2. All right. Then I need beta. So beta, I've squared 2 over 2. I know my reference angle would be pi fourths, and it's negative. So in the circle, sine is negative in quadrants 3 and 4. So my third quadrant pi fourths angle is 5 pi fourths. And then my fourth quadrant is 7 pi fourths. Okay. What questions do you have? Anything? Okie dokie. Let's look at number 8. Number 8, I'm back to using the whole circle. When I look up here, I've got a half angle. Pretty sure I want to get rid of that first. So I will have cosine x plus 2 equals. So when I look on here, I find sine of theta over 2. There's only one option there. So I'm going to write that one down. So I get plus or minus square root of 1 minus cosine x over 2. So I think it's way more obvious here than on the one we did on the front that I'm going to need to square both sides. So I'm going to square both sides. Now, if this side had just been a 2 and not cosine x plus 2, I wouldn't need to check my answers in the end, because this plus or minus, this is already kind of taken care of because it's a square root. But since I'm squaring an one of my actual variables, then I'm going to put a little star here because I'm going to need to check myself in the end. When I square cosine x plus 2, it does not become cosine squared x plus 4. If you don't know why, I don't know how to help you at this point. You're going to have to figure it out. All right, so cosine squared x is what we actually get once my board catches up with me. There you go. Cosine squared x plus 4 cosine x plus 4 equals, then on the right-hand side, when I square that, since it's a square root, I just get whatever's underneath it. So that's 1 minus cosine x over 2. Then I'm going to multiply through by 2 to get rid of that fraction. So that gives me 2 cosine squared x plus 8 cosine x plus 8 equals 1 minus cosine x. 2 cosine squared x plus 9, because I'm moving everything over to the left, 9 cosine x plus 7 equals 0. Okay. I have a quadratic that you're totally capable of factoring. A is not 1 though, so you got to do whatever it is you do when A is not 1, whether it's by grouping or whatever way. I don't care as long as you can do it. I'm not going to take the time to do the grouping. I'm going to do it the old school way, and I'm going to talk you through it again because on this particular problem, it makes the old school way pretty easy. And if you're already really good at factoring, I highly suggest that you try and do some of them the old school way because that'll be a lot quicker for you. And the more you do it, the easier it is, everything is to see. So I'm not saying you have to do it this way. I'm just going to talk you through it. The reason this one is easy is because this isn't 1, but it's a prime number. So that means I know that one of them has to be 2 cosine x, the other one has to be cosine x. Then since this is positive, that means the signs are the same, and since this is positive, they're both positive. So I don't have to make any sign decisions there. Since that last number is prime, I know 1 and 7 are my choices. That's all I got. I don't have to play with a whole bunch of them. It's just 1 and 7. I just got to figure out where they go. So if I think about putting 7 here, that means at some point I'd do 7 times 2, which is 14, and then this would be 1. That's not going to give me 9 in any way. So 7 can't go here, which means it has to go here, and I'm done. But I would always check myself. So I got 7 times cosine and 2 times 1, so that's 7 and that 2, that's where the 9 comes from. And it's factored. Again, not saying you have to do it, but you got to be able to get to that point, however it is that it makes sense to you. Now we're going to solve this. Then I get 2 cosine x equals negative 7. Cosine x equals negative 7 halves. Is cosine ever going to equal negative 7 halves on your circle? No, because we can only go from negative 1 to 1, right? So that's nothing. Then I get cosine x equals -1. Well, I know that cosine is -1 at pi, so x equals pi. But remember, we put a little star there, or whatever you want to do to make it right out to the side if you need to. Check answers, whatever, so you don't forget. I need to check my answers. So I'm going to take this and I'm going to substitute it into my original one right here. So that means I'm going to get cosine of pi plus 2 equals sine of pi over 2. Okay, I'm just substituting it into the original. If I get a true statement, I'm good. If I get a false statement, then I'll just have an empty set here. So cosine of pi is -1 plus 2. Sine of pi halves is 1. So this gives me 1 equals 1. True statement. So this is my answer. And I'm done with that one. What questions do we have? Anything? All right. We're good? Make sure you're finished writing. Okay. Well, let's look at number 9. Here I'm going from pi to 2 pi. And I've got half angles, so I think I want to replace both of those. So I'm going to go ahead and write down this 1/2. Then I'm going to look at the tangent of the half angle. That one's where I have 3 choices. Okay, so when I'm looking at those, I'm thinking choice number 1, if I can avoid it, I want to avoid it because it's a yucky square root. Then the other 2, they don't look too terribly different, but I would prefer for my denominator to have 1 term. Usually that's what makes it a little easier to work with. So I think I'm going to go with my second option there. And instead of tangent of a over 2, that's going to give me, I'm going to multiply this, it's going to be 1 minus cosine a over sine a. Then minus, and then I'm going to need to substitute for that cosine half angle. So that's cosine squared of the half angle, which means you just take the half angle identity and square it, basically. So I know that that whole, whatever I substitute in for the half angle, it's going to end up having to be squared. So I find cosine of theta over 2. There's not more than one option there. Just, it is what it is. So this is plus or minus square root of 1 plus cosine theta, although I'm using a and not theta, so let me do that correctly. 1 plus cosine a over 2. And that's squared, not because I chose to square it, but because it's there in the problem itself. Then I have times cosecant a equals 1. Okay? So yes, we're squaring that square root, but that's not something we chose to do, so we don't have to check our answers. It's just like if you happen to take a square root in the problem, you don't have to put plus or minus. It's when you introduce it. So when you decide to square both sides, that's when you have to check your answers. That doesn't count here. Okay, so if I multiply this, if I just multiply straight across, this gives me 1 minus cosine a over 2 sine a. Minus, and then when I square this, I'm just going to get what's underneath, so that's 1 plus cosine a over 2 times, and then cosecant a I could make into 1 over sine a, and I think I want to do that given this denominator here, so I'm going to make this 1 over sine a, and that's going to equal 1. Any questions about where anything came from? Remember, I'm getting this stuff from here. I'm not making it up, and there's no magic. So when I look at these, I could rewrite this again, but when I rewrite it, that's just going to be 2 sine theta in the denominator. So of those 2 fractions, I have a common denominator. So I'm going to go ahead and put them together. And so this will be 2 sine a in the denominator. In the numerator, this 1 is being multiplied by all of that, so there's like parentheses here, right? So it really doesn't do anything to it. But the parentheses are still important because I have this minus. So I'm going to do 1 minus 1, that zeroes out. And then negative cosine a minus cosine a is going to give me negative 2 cosine a. And then all that equals 1. So it's condensing down kind of nicely. Usually the uglier it gets at the beginning, like the easier it is to simplify everything. Then the 2's cancel. I'm still going to have the negative. Cosine over sine is cotangent. That's equal to 1. But I need my trig to be positive, so I'm going to multiply through by a negative 1. And I'm going to get cotangent A equals negative 1. I would rather think in terms of tangent, so I'm going to make that tangent A equals, and the reciprocal of that is negative 1. When tangent is 1, the reference angle is pi fourths. In these two quadrants, tangent's negative in the fourth quadrant, so I only need my fourth quadrant pi fourths angle, which is 7 pi fourths. Okay. What questions do you have? Now, I did a bunch of examples because a bunch of different things happen, and that doesn't mean that every question you have on your assignment is going to directly match one of these. That's one of the reasons why I did so many, because you need to know how to kind of think through it. All right? Any questions at all? Remember to use your notes. All right?